Hi, and welcome to the workshop ImSwitch for developers and microscope builders. My name is Xavier Casas, and I'm from the lab of Ilaria Testa at KTH in Stockholm, Sweden. And today I will start introducing the workshop and go through the different modules. So we divided the workshop in different sections. First of all, I will go through the introduction and presentation of material, including GitHub, the read the docs page, and the paper, installation and the configuration files. Then I will explain the architecture of ImSwitch and how to develop different modules, including for those for supporting more devices, but also those related to graphical interface components. Then I will include one section linking ImSwitch with Mapari. So what are the different ways of developing widgets or plugins that will have access to both software? Then I will explain the scripting, which is a module for developing scripts that will control the hardware and the software in ImSwitch. And finally, I invited some people to explain to you their experiences and developments that they did. ImSwitch is an open source software, and you can find it publicly available in the GitHub repo. Here we can find a README file in which we explain the statement of need, the instructions for installation, testing, and contribution. And then we are using read the docs for further documentation that I will go through just after this. Then you can also open different issues if you have some questions or you find bugs or want to suggest new features, for example. And if you want to start a discussion in a topic that you feel needs to be discussed, you can open a discussion thread here. Then we have the read the docs. Here we explain a bit more all the different parts of ImSwitch and more from a user perspective, including how to install it in the different possibilities, how to contribute. Here we also explain the graphical interface, what are all the different sections, and each of the widgets further explained. And we have here a section for use cases in which we have the different microscopes that we are currently using with ImSwitch and all the different instructions so that you can also reproduce it. The scripting module, as I said, it's a way to develop scripts in Python that can manipulate functions in ImSwitch that are exported. You can export your own functions, but you can also find here what are the different functions that are currently being supported. For example, getting the detector names, the laser or the positioner names, running a scan, setting lasers on and off, and setting the different powers, and also with the different positioner, axis. Anyway, I will go through this more in detail also in the scripting section. And then here we can have some documentation about different modules and the data sets. Now we are using HCF5, in which we can save the image data, but also we save different metadata, which we explain here, which are basically all the information about the detectors, such as the pixel size, the readout time, also lasers, the power, and if they are on or off, the positioners, and also further information about the recording and the scanning. In this section, we also explain the configuration file that I will also go through after this. And basically, each configuration file is defining what graphical interface ImSwitch is going to generate and also what setup you're going to use. So in this way, we can use ImSwitch for different setups. And also the available manager, so what devices are supported. And finally, in the paper that you can find if you click here, I find this as more as a technical documentation in which you can really understand what is the architecture, what are the different key components that I will also go through in this tutorial, and having this sketch that I usually find useful when you are developing new plugins. There are different ways of installing ImSwitch, and it depends whether you want to use it as a user or as it is, or if you want to develop some modules. If you want to download a release, you can go to the release page in GitHub. And here you can find a zip file with the executable files for Windows. Or you can also go to PyPI and do pip install ImSwitch in a Conda environment, for example. So this will download the latest release. But since we in this workshop want to install and develop our own widgets and devices, we will install it in a different way. So we will open an Anaconda terminal, and we will follow this instruction. So first of all, I suggest that you create a new Conda environment. For example, switch with Python 3.9, for example. Once we have created a new environment, we can activate the environment. And then the idea is to clone the source repository from GitHub. So I will clone it in Documents and GitHub, and the workshop folder. So this is going to clone the repository from GitHub to our local computer. And finally, if we want to install all the requirements for ImSwitch, we can run this command, pip install -r requirements dev for the developers. So now we are all set. We have all the code in this folder, and we have a Conda environment with all the requirements installed, so we can start. So as I said in my presentation, the configuration file is an essential part of ImSwitch because it's going to determine what type of graphical interface it's going to generate. It can be from very simple configuration files, such as this one, where we have one laser of a certain vendor or company. Then that is using a driver and a configuration port or a digital port with a certain wavelength and set of powers. And then ImSwitch is going to generate just this graphical interface. Or we can have more complex ones. But the basic idea is that we are going to have a list of all our hardware, for example, all the detectors and their properties, lasers, positioners, and also all the available widgets that we want to have. So for example, if we don't wish to have the image display, we can remove this line here. So I created one configuration file for our workshop in which I'm only using one detector. That is going to be a Thorlabs camera that I have here, and where we are only going to use the settings view and the image widget, plus the FFT widget that we are going to code also during this workshop. But configuration files can range from this simplicity to far more complex ones. In the presentation, I showed you that we can have setups without an image viewer. In this case, for example, we will only have the laser control and the scanning module. And we use this for photo switching experiments. So we only want to control several different lasers and different pulses that are going to trigger those lasers. This corresponds to this type of configuration file where we just list all our lasers that are quite some. In this case, also some positioners for the different axes and stages. together with the communication port, the RS-232 device. And here are all the available widgets that in this case are only two, the laser and the scanning. Each of these lasers, for example, have different parameters. Analog and digital lines are for whenever they want to be triggered from an external data acquisition card, for example, a National Instruments. The manager name is going to be the type of class that is going to control this laser. In this case, since it's controlled through an RS-232 device, we can have all the lasers controlled to the same ports, but with different indexes, for example. And the wavelength is going to then determine also the color in the graphical interface. This is a bit more complex, and in this workshop, I will work with a rather simple one, but I just wanted to let you know that it can be as complex as your graphical interface needs to be. Another example is our stat setup, which has many different devices. And we have here the configuration file. We can have different detectors. They can be either point detectors that Jonathan is going to explain more in his presentation. Also, they can be combined with different cameras, either for acquisition, like a wide field camera, but also external cameras, such as a focus log camera, which is going to be used for different separate widget to control the focus of the stage. And also we can have as many lasers as we want and different positioners, not only stage scanning, but also galvo scanning. And for this, we are using National Instruments to control them all and to trigger. The first time that you run ImSwitch, you will find all these configuration files in documents and ImSwitch config. So if we go to ImControl setups, here we are going to find all different configuration files that I showed you, and we can also create new ones. So I create this one for the workshop, for example, in which we are going to integrate a Thorlabs camera. But apart from that, we also have other different folders, such as the different scans that we can have, that right now we don't have any, but it's for the scanning module and the triggering of the NIDAC, the SLM patterns for the spatial light modulator, different recordings. If we don't, we can either save the recordings in this folder, or we can change the folder. And also different scripts. Here we have the example scripts, but we can also build new ones and save them here. The idea of having a separate folder is that if we update ImSwitch, or we change the version, or we want to create a new branch, all of the different versions of ImSwitch are going to use the same folder that is going to be in documents. And then we are not going to lose all these important files. And here in config, we have two different files, ImControl options and ImControl modules. In ImControl options, we are going to have the setup or configuration file that we want to run, and also the output folder in which the recordings are going to be saved by default, but we can also change that after initializing ImSwitch. And also we can state in modules.json the different modules that we are going to have. For example, ImControl is to control the hardware, reconstruct is another module that is going to reconstruct the images and scripting. But we can also hide those, and we could also create new ones for the ones that want to have extra modules. In this file, that is in ImControl model and setup info.py, we have all the information in code that is going to read all these parameters from the configuration files. We can also add new ones, and we can also update it, but I will not focus much into detail in this, but just so you know that this is where you will find it. And this is going to basically convert between the JSON configuration files and Python attributes. That you know a bit more about the documentation, the installation, and the configuration files, let's get into the practical example of developing new modules into ImSwitch. And for doing so, we have to have very clear in our minds the architecture of ImSwitch. As I said in the presentation that I suggest that you watch, we have different components: the view, presenter, and the model. The view is that component that is going to be related to the graphical interface elements. those are different widgets. For example, the Fourier transform module that we're going to create is a widget, or the image viewer, or the recording. So there are different widgets that take different functions in the user interface. Each of them is going to have a widget controller that is going to take the actions from the user and either send them down to the hardware through the master controller. So for example, if we are using a laser and the user is clicking a button to turn it on, this will communicate with the master controller and send it to a manager. And or we can also have widgets that communicate with each other through the communication channel. And then regarding the managers, each manager represents a different device. So what we want to do in this workshop is to integrate a camera. It's a Thorlabs camera that I have here. And for that, we are going to have to create a new manager corresponding to the specific detector. And we will also do a graphical interface widget and its widget controller to perform the Fourier transform of those cameras. I'm using this camera, but you can use any other camera that you want. And since it's well separated, the view from the model, that's one of the beauties of this architecture, is that it's not really going to matter which manager or which device we are using. It's going to work either way, as long as we state it in the configuration file. For that, as I said, we will have to generate a Thorlabs camera manager. That is going to be a specific type of detectors manager. I also explained this in my presentation, but a detectors manager is going to be a type of multi-manager that is going to handle whenever we want to use many different detectors at the same time, and for it to be integrated in Apari and the image viewer. That is going to be part of master controller that's going to have access to them. And as long as this will be a type of detector, they will be automatically integrated in the graphical interface. But the second part of the workshop will be to create a widget for calculating the Fourier transform, which is a type of transformation of an image. And we are going to do the widget and also the controller. Now that you know the architecture of ImSwitch, you can see that the file system is quite related to it. First of all, we have all the different modules: ImScripting, ImReconstruct, and ImControl. We are interested in ImControl because it's the one for hardware control. And then inside this folder, we have one for controller, that is the presenter, another for the model, and another for the view. The first step that we want to do is to create a new device manager, and that's going to be in the model. So if we go to model, we have here all the different managers. So inside managers and inside detectors, here is where all the detectors managers are going to be. And what we want to do first is to create this file, Thorlabs or ThorCam manager. That is the manager that is going to support devices such as the Thorlabs camera that I have. This is rather complicated, but it's just to show you that we have a type of multi-manager called the detectors manager, and this is going to have a list of detectors that is this sub-managers. This is just to show you that whenever we create a type of detector, it's going to be included here, and therefore included in the widget that is going to display the images. Each detector is then a subclass of detector manager. And the detector manager is a class that is defining certain functions that need to be re-implemented in our class. For example, the update latest frame, in which we are going to take just the latest frame for displaying in the live view, setting different parameters, such as the exposure time or so, the binning in case our camera has binning, and then we have some properties, and yeah, this get latest frame, that is the one that is going to call update latest frame, and then get chunk is a bit more complicated, but it is whenever we want to store it into frames, and we don't only want to take the last one, where we want to take the whole buffer at the moment, then we're going to call this function from the widget. So it can be as simple as you want, but you can make it as complicated as you want by redefining all these functions, but it's not necessary. So what we will do in this workshop is to just create a ThourCam manager that is going to display the frames that we get from the camera into the live view. And then I leave it up to you if you want to implement all the different functions for setting different parameters and getting more complicated. If you want to check just for reference, you can check, for example, Hamamatsu manager that is quite complete in order to see all of the possibilities that you can implement or the other ones. And the idea is that also in the future, we want to be able to use directly the device support that other libraries offer, just such as Python microscope. And for this, Jacopo is going to explain what he did in his developments a bit after. I will share this file, but in order to do a Thorlabs camera manager, we have to create this class that is a subclass of detector manager. And then in the initialization, we have to add this because it will be already done automatically. Detector info is all the information that has been gathered from the configuration file. And the name is just the name of the camera. Then we can have, for example, here a logger if we want to send messages for debugging or errors into the command line, but it's not necessarily. And one of the most important lines is the line that is going to return the object of the camera. And for this, we have this function get object. And then as a parameter, we are sending the camera list index. So for initializing the camera, what I usually try to do is to see if there is another library that is giving support from the driver perspective to the camera from Python. And in this case, I found PyLab that as a device, I have the camera that I want, and I can initialize the camera. I initialize the camera in this get object function. And in here, you can see that there is a try and exception. In case it works, it's going to return the camera. And in case it doesn't work, it's going to return a mocker, which is just a type of fake device that we want to use in order to debug. But this is optional. And I suggest that in case you have errors, you can comment these lines, because then you're going to see what error you have. So it's better to start this way. And now it's just a matter of translating the functions that ImSwitch needs from the functions that the library of the specific device is giving you. And I checked the documentation, and I know that in order to return a camera object, you have to run this function, for example. And then it will be a matter of substituting all these functions by the real implementation of each camera. So getLatestFrame is one of the most important functions because it's the one that is going to be called from the widgets to display the images into the live view. Set parameter is to set all types of parameters, such as exposure time, the pixel size, and so on. Get parameter will get the parameters from the camera. Get chunk, it will be used to get the buffer of frames, and it will be for the storing into a file. And then we have start acquisition and stop acquisition whenever we want to start and stop acquiring those images. Then for finalizing, this is going to be run whenever we quit and we want to close the driver. Then we have, for example, cropping in case we want to crop, and all these functions are already integrated in the widget. So in this workshop, I'm going to try to make it simple. So we are going to try to just returning get latest frame a snap of the image. So self.camera.snap. And this I check because camera is going to be the object that is returned by this function. And I know that this is coming from this library. And in this library, I read that in order to get the latest or a snap, we have to run this command. So we'll just translate that. Then it can get more complicated. Another thing that I want to do is in this function, starting the acquisition. And in this other one, stopping it. So it's having a bit of patience and reading well in the documentation how to perform each function and writing it in the right place in ImSwitch. Then for cropping, it's very useful, but I will not go into that. And I think this should work. So the graphical interface has started. This is the image viewer, the detector settings, and the view settings. And if we click live view now, we can see the images that are being obtained from the camera. I have the camera here with a post-it. So if I take away the post-it, we can see that the counts get higher. So it means that it's properly integrated. So now we want to create a widget and a controller that are going to perform the Fourier transform of our images. And the steps that we have to do is, first of all, create an FFT widget that has to be a subclass of this widget that we can import with this line from our base widgets. Then we also need to include it in the initial init file inside the folders of widget. So here we have FFT widget there. And we need to do the same for the controller because each widget will have a controller. So we put it in the initialization file of the controller. And then we also create a controller that has to be subclass of widget controller. So this is the first step that I do. And to start, you can create an empty controller, and then you can start working only in the graphical interface. So I created this where it's a widget that has a check for showing the FFT. And then inside, I embedded a view box in order to visualize the image. And this is not important how I did it, but basically it has a view box, a histogram, and the image. But you can do in your own way. This is just an example. And then I create a grid, and I have the two components there. And then I have two functions, one to get the image, and the other one to set the image, and one to show the check. I mean, to return if the check is checked or not. And then another thing that you have to do is going to the main view that is located here, ImCon main view, and add a line for the FFT. And it depends if you want it in the right side of the graphical interface or in the left side. In this case, I want it in the right side, so you just have to create this. And since we call this FFT controller and FFT widget, this has to have the same name, so FFT. So, and then I usually see if it runs correctly and if I have the module in the right place. So indeed, now the module is here. Since I hide all the other modules, it doesn't look perfect, but for now we will leave it like this for this workshop. And then we can start working on the controller. So for that, we have to think when the widget is going to communicate with the controller, and it's whenever the user clicks that they want to show the FFT. And then we create one signal called signal show toggled that is going to be connected to when the checkbox is toggled. So here we linked the checkbox signal with our own signals. And then we go to FFT controller, and then we have to link the same signal that we have, show toggled, with the function for performing the FFT. So here I created a widget, a FFT controller that will basically perform the FFT whenever the user clicks that button. And then basically this will be on. And then there's also something that happens here, that is we have a specific type of controllers that are called live updated controller. And it's also part of our base controllers. And this will mean that every time that there is a new frame in the live view, there will be a function that is called, and the function called is update. So then we just have to here write the codes. If the checkbox is active, then we have to perform the FFT and set image in the widget. And that should be all. We can see if we activate the live view and then we click here, show FFT, the FFT will be shown at the same time as the other image. And then we can take a bit of light and we can see how it changes. The question is, what if instead of having a separate widget with the result, so showing the view box, the result of the Fourier transform, we want to update Napari, create a new layer, and add the result of the widget there, only the image. And for that, we have a special type of widget called Napari hybrid widget. So if we add here Napari hybrid widget, the only thing that we have to do is initialize the layer to none, and then get image and set image are going to be slightly different. So we are going to clear in case there is no layer or the layer is not in the list. It's going to access self.viewer, and this is going to return the Napari viewer dot add image. Otherwise, it's going to update the layer. And then also something that we have to do is to change this function by post init. So, and then we can remove this also. This is just by how the widget is made. So we can then run ImSwitch. So now our widget here is very simple. And when we click live view and click show FFT, we can see that there is a new layer in Napari, which is showing simultaneously the FFT at the same time as the live view. So here we can see. And this you can do with any type of processing, as long as you code it in the widget and then you do it with this type of architecture, then it will be included in this layer. And I also wanted to quickly go through other ways of connecting or interconnecting Napari and ImSwitch. One is, for example, this type of widgets that we can add in the viewer. And for example, this one we find very useful to align each channel to another. So whenever we click, one image is moved respect to the other. This is very useful when we are doing multicolor imaging, because usually the channels are not aligned because of aberrations, and also because of the natural path of light where they go through. How this is done? So this is done by having a widget that is a subclass of Napari base widget. And we usually have those kind of widgets in Napari tools inside GUI tools and the view. So I will not go into detail, but you can check here. And then in the image widget, here we are going to add to the viewer the widget. So it's done in a slightly different way because we want to have it inside Napari. Regarding the scripting, the first thing that I would like to draw attention to is this page in our read the docs, in which you can see all of the functions that you can access from the scripting module. And they are mostly related to either turning on and off lasers, moving positioners, getting the names of our positioners, detectors, lasers, getting images, and so on. And in order to develop scripts, you have to go into ImSwitch. And here you have the three main examples. So one is in order to import a script that is in another file. And another one here is to perform a recording. So in order to access the functions, you just need to type api.imcontrol. And the name of the function. And also, if you go to the GitHub repo and discussions, there is a discussion called scripts, where I have uploaded some of the scripts that I use. For example, how to turn a laser, move a positioner, and take an image. Or how to do photophysics experiments by having a for loop that is going to change the powers and scanning. And I hope to be uploading more. If you want to export your own functions, what you have to do is whenever you create a controller, you import this line, imswitch.command.model import API export, and then you will have to put this decorator in the different functions that you want to access. And then this will mean that you can access them from the scripting. So I hope that you followed and you found useful the workshop and the first part, at least, where I introduced the material. I also guide you through the architecture and how to develop devices and widgets, and then how to make use of the interaction between ImSwitch and Apari, and a brief introduction to the scripting. And now I will leave you with Jacopo, Jonathan, and Benedict that will share their experience and developments.
Hello everyone, my name is Jacopo Bramo. I'm a PhD student at the Leibniz Institute for Photonic Technology in Jena. And today I will show you how to integrate Python microscope into ImSwitch as an external layer. And later on I will show an example application which we have in one of our labs in Jena. So first things first, what is Python microscope? It's a package for microscope hardware control, which can provide a common and easy to understand interface for devices sharing common functionalities. Supported devices so far range from light sources, cameras, stages, and so on. But you can find a full documentation about the package on their website. We will use as an example and create the laser control functionalities of Python microscope to create a single ImSwitch manager which can integrate all the lasers supported by Python microscope without having to specify the exact device that we want to use. In this example, we will refer to the Toptica I-beam smart laser, and we will show you how I integrated the manager into ImSwitch. As you can see here, we have the PyMicroscope Laser Manager, which is a generic manager for all Python microscope laser devices. And these are discerned by using the manager property PyMicroscope driver, which can specify the exact module and class name referred to the laser that we are interested in. And secondly, we have the digital ports properties, which specify the name of the COM port which we need to connect to. The manager automatically detects the type of device that we want to integrate into the setup, and then it instantiates it as a local object, so we can access its properties directly. And since the interface of Python microscope for the lasers is common for all devices, we don't need extra code to define the laser itself. So in order to make use of the laser, we have to define the setEnable function, the setEnable method, and the setValue method. And then both methods refer to common functionalities of Python microscope laser devices. So in order to enable them, we don't need to access any kind of information related to the laser. We just need to call the either enable or disable functions to enable or disable the laser. And in order to set the power output, we can directly set one of the properties, which is the actual power of the laser, by calculating the current value set as an input parameter and divided by the maximum power which we record at the beginning of the initialization of the class, because it's represented as a percentage of the maximum power that the laser can output. It is also important to define the finalize function, which is not an abstract class function in the manager, but can be added in case it's needed in order to shut down the laser and to allow other processes to take care of accessing the laser if necessary. So this is an example of the configuration file to represent the laser manager that we want to instantiate. And as you can see, we don't refer to any analog channel or digital line for our laser, but we make sure that in the manager properties, we refer to the specific driver that we are interested in this case, the Toptica I-beam, and the required digital ports to access the serial line to connect to the laser. Now I'll show you an application example of how to use ImSwitch by creating a real-time median filtering with an interferometric scattering microscope. This is the IceCat setup in one of our laboratories. We have Aximia CIB64 family camera, which can reach up to 3000 frames per second at 1.1 megapixel. And we control this camera directly via ImSwitch with a custom detector manager. Then secondly, as mentioned, we have a Toptica I-beam smart laser with a maximum power output of 130 milliwatts and a maximum modulation frequency of 1 megahertz. Then we have a series of piezo stages, both for micrometer movement and nanometer movement on all three axes, and both stages are controlled via a custom ImSwitch manager. So the objective of this experiment is to create a TIFF stack to use for computation of the median filter to apply to our recordings. We use as a reference sample a 40 nanometer gold nanoparticle in water. And we use this to perform a multidimensional acquisition, meaning that we record a single image at each position of the XY stage and create a stack of them. And then we will use NumPy to calculate the median of this stack, and this will be used as our median filter to apply to our recordings. So we have to store the created filter in the detector manager and use it for real-time processing. And we will show how this works by making a test record. So in this script example, we define a series of parameters needed to execute the experiment. And specifically, we will define the name of the positioner, the name of the camera, and the number of frames which we want to collect. It's also important to define the minimum step of the stages of the XY stages in order to have the maximum number of positions, final positions that we want to get. Then we can set also the number of another number of parameters, such as where to store the files, and then we calculate the number of movements based on the number of frames that we want to collect. And finally, it is important to call the local ImSwitch APIs in order to set the positioner step size for the X and Y stages. It is also important that beforehand launching the script, you have to make sure that your sample is in focus. So to create the stack, we will use one of my custom APIs that I developed specifically for this example in ImSwitch in order to get the instance of the detector that we want to use for the recording so that we can access the low-level functionalities of the single detector. In this case, we will start the acquisition, and with two nested for loops, we will move the positioners of one position for each axis, both on the positive and the negative direction, and then record an image and append this image in a local buffer. After recording all the images that we need for our median filter generation, we can stop the acquisition, stack the images on the local buffer, and then calculate the median of this stack. So you can see on the left the recorded stack that we collected, and on the right the relative median filter generated by the calculation. Now we can apply this median filter that we created to the single recordings of the detector, and by doing so, the Ximia detector manager that I implemented has a local object that can be referenced as a median filter. And after that, we can set both the recording folder and the file name, and then we can test the efficiency of our medium filter by recording 100 frames and store them as a HDF5 file to evaluate if the recording went well. It is important to delete the medium filter within the detector in order to not affect future measurements. And here, as you can see, it's the recording that we collected from the detector with the medium filter applied. And remember that this is a real-time application of the filter on the recorded images. So in summary, we were able to implement both Python microscope into ImSwitch as a local manager and without having to do particularly complicated code. And in the future steps, we will also be able to integrate both the camera and the stage control into ImSwitch from Python microscope. Finally, we have shown how Python scripting within ImSwitch can be used to have a reusable code to attain quick measurements with low effort. Thank you for your attention.
Okay, so hello everyone, I'm Alvelid. I'm a postdoc in the lab of Eliar Testa at KTH's SciLab lab in Stockholm. And in this part of the workshop, we will be talking about steady imaging in ImSwitch and the requirements for this and the developments that I've been performing in order to enable this. In the end, I will also briefly mention event-triggered steady imaging, which is an acquisition method I've been developing that was really enabled and benefited a lot from the architecture of ImSwitch. So in order to perform steady imaging, what are the requirements? Well, we need all the point scanning aspects, such as the scanning and how we generate our images that are needed for point scanning. So this includes smooth scanning signal generation. So we're using galvanometric mirrors to scan very fast. And then you need these kind of smooth scanning curves and not stepwise functions, which you might be able to use, for example, for stage scanning. These signal generations also has to be modular to different inputs of the scanning, such as the image size, the pixel size, and so on. It also has to be able to adapt to velocity and acceleration limits of certain scanner modes. So the way it's implemented is in a piecewise signal generation, and you can see it generates signals like the one to the right here, where in green we have the X position and in red we have the Y position. If we zoom in to one part, we can clearly see these different pieces, such as the initial positioning, the actual linear line scanning that we have here, which is actually the only part which is generating a signal that we want for our image, and a flyback, and continuously repeating this for different lines. We also need to integrate both time-lapse and volumetric imaging, so basically multiple axis recordings into this in order to be able to perform this as fast as possible. But I will not talk so much about this. I will move forward. We also needed, for example, a point detector signal reading and a pixel assignment to the image. And this is also crucial and very different from how we would perform camera-based imaging. And this needs to be synchronized also to the scanning to know that we're taking the right signals that we get and putting them in the correct pixels. But what I would like to focus a bit more on is the control of a spatial light modulator, which was crucial also for using STED in our setup. Because we use this spatial light modulator to control the depletion patterns that we use to deplete our signal instead. So I've been developing a widget to control an SLM. It works by controlling and generating two separate masks. And we use this to create two face patterns at the same time, such as a donut and a top hat. But it can easily be modified to just include one of these masks, for example. We also can perform aberration correction in this. And you see here, this is clearly aberration corrected based on the parameters that you input in this dictionary viewer here that the user can change and see how they change in real time. You also have buttons in the control panel here for changing the patterns, such as this, and moving the patterns on. So I would like to focus on how you can use this widget and implement your own face pattern. Say that you want to create a face pattern such as sinusoidal wave pattern. How would you go about doing this? Well, there are certain steps required for this. First, you need to define the mathematical functions for your pattern. And you need to implement them in the SLM manager, which is basically the backend calculator. It calculates all the parameters for your face patterns. You also if your pattern needs certain additional parameters that you want the user to be able to control, you also need them to add them in the SLM parameters tree that I just showed you in the widget. You You also need a button to be able to switch to your pattern, and you need the SLM controller to basically coordinate all of this control with the SLM manager in the backend. So if we look at the code for how to be able to perform this, we can start with the SLM widget here, which is based on the base widget class. It takes, for example, here it generates these parameter trees that you saw in the widget. And this is where you would add, if you have parameters specific to your type of pattern, you would add a parameter for that here, such as, for example, the frequency or the phase of your sinusoidal pattern. You would also add a button here to be able to switch to your pattern, and you can name it whatever you want, and you add it to the layout of the control panel. And this is basically what you have to do in the widget. In the manager, the SLM manager, the backend controlling part, this is basically where we can create all our patterns. So we actually create 4 different patterns. I will not go into detail of why, but basically one of these is creating the patterns that actually generate the light pattern that you want. For example, your sinusoidal pattern, if this is what you want to implement. You have a function that basically switches a mask between different types of patterns. You see all of them here. And in a separate class, that is actually the mask, and the objects that you generate from this, you have functions to change between your different patterns. We can take as an example here the top hat, where you actually generate different parameters, grid parameters, or distance from a center position that you use in order to create your pattern. And this is actually what happens here. So here you define certain functions using these grid parameters. And this is what generates your mask in the end. And here you can also have parameters such as here we use a sigma parameter that is actually existing inside this parameter tree, as I told you. So in order to do that, also if you have that for your specific pattern, you need to implement a separate function that actually defines this and sets them when the user presses apply after changing these values in the parameters. In the SLM controller instead, you need to connect this together. So you need to add a line like this that actually connects the click of your newly created button in the widget to the set mask function with a certain mask mode parameter of your choice, which you also would have to add. So this function in the end just calls the different functions in the SLM manager that needs to be called in order to generate your new mask, and it updates the displayed image. So that's actually it for being able to generate your own SLM pattern. So it should be fairly easy to add whatever type of mathematical function that you want to create your pattern from. So I would like to briefly then mention, as I said, the event trigger state imaging and how we can perform this in ImSwitch and what was required for this. So here we can combine wide field imaging as a very fast imaging method to monitor our sample with real-time analysis. So we have an analysis pipeline that actually runs on every wide field frame that comes in the tens of millisecond scale. And if with this pipeline we detect something taking place that we're interested in, we actually go there to perform steady imaging very rapidly inside the tens of milliseconds after this event taking place in a small field of view. So for this, I've developed a control widget in ImSwitch that basically is able to control this real-time analysis. You can exchange this pipeline to whatever you want, and also gives the user live feedback on how this pipeline is performing. So I thought I would also mention briefly how you would go about to implement your own analysis pipeline here. So basically in the user interface, the widget looks something like this, where you have different parameters to control the acquisition method. But specifically here, you have a drop-down list where you basically can find all the analysis pipelines that are available, and you can load them. And it also loads a certain footprint of this in terms of these parameters, which the user can modify and with live feedback actually see how these are affecting the detection of events. I should also mention briefly that this is available in a separate repository in GitHub, as well as being implemented in the main ImSwitch repository. But here you can find some additional information on how to control and how to modify this to your liking. And I also like to mention then, how would you go to implement your own analysis pipeline? So if you're interested in using this method, you likely have a type of event that you want to detect. So you create your own Python function in a Python file with an analysis pipeline that actually detects this event from an incoming image. You add this in the ImSwitch user documents folder in a certain folder that you can create if it's not already created. And this pipeline that you create has to have, for example, the current image as the input and certain other things, and can also take optional input such as how many pipeline parameters that you want. So this could be different thresholds or different distances and so on that you use in the analysis pipeline. And it has to output then the coordinates of the detected events if it detects any. So in the code, to do this, we'll do something like this. We have our widget and controller for the when-triggered imaging. And in the widget here, we have the folder defined where you actually find all the analysis pipelines. So this is where you will have to put it if you develop your own pipeline. And it actually takes all of these pipelines in this folder and adds them to this drop-down list. And then in the controller, when you load a pipeline, it actually loads both the module, which is actually the function itself then, and also the signature of this function in order to get all the parameters, right? So all these optional parameters that you put in your pipeline is actually loaded into the GUI automatically, so the user can modify these with live feedback during the experiment. So if we look at one of these pipelines, it looks something like this. You can import whatever packages you want. We have one line that defines all this required inputs and the name of your pipeline. And then you have, following that, all these optional parameters. Then you have your pipeline, which in this case is one that detects rapid signal spikes, such as those from fluorescent sensors. So this performs certain pre-processing and a peak detection method before sorting the peaks that it actually detects. Based on certain criteria. And if it detects an event, it adds it to this coordinates list. And then you need to have a return statement that looks something like this in the end. So that's actually it for being able to use this and detect the analysis, detect events that you're interested in with a customized analysis pipeline. So with that, I would like to thank you for your attention for this part of the workshop, and also like to thank the Testa Lab and the people that have been involved, of course, in the ImSwitch development. Thank you.
So hello everybody to this I2K workshop presented by Xavier, and I'm very happy to present our take on that. So UC2 maybe is familiar to you. It's a modular open source toolbox for optics, in particular for microscopy, and we have a bunch of modules that enable us to build arbitrarily complicated setups, what you see here, and a few of them have control steps. What you want to do is basically, for example, control a motor or turn on off a laser or an LED. And to simplify that, we started working with ImSwitch, which is quite surprising because back then I was a reviewer as my surprise on the Journal of Open Source Software. It's a very nice way to communicate software projects, so definitely have a look. It's very interesting in the YouTube-based manuscript. So, and what you have here, for example, is just one example how you can use microscopes similar to a Python package. So you have a bunch of different modules. You can put them together to assemblies. In this case, it's a rather simple one where you have just an inverted bright field microscope with an LED array to illuminate your sample from different directions, for example, in order to have phase contrast microscopy. And this was the first idea where we wanted to see how macrophages developed from monocytes, so basically the differentiation process. Back then we only used a Raspberry Pi, and so the whole setup was pretty much self-contained, not that versatile, even though the modules itself pretty much stayed the same from the form factor side here. And so the next step here is then, well, you can just reorient it, the different modules. That's beautifully done by Ando Serra, who's part of Helge Eber's group in Berlin. And what he was able to do is basically single molecular localization on a 3D printed microscope, which is very surprising because what you have in the end is super resolution for a dime. That's what I'm talking about. And for this, you need all kinds of different things. So you need a good microscope from the hardware side. So you need triggering, you need lasers that are synchronized with the camera, etc. And all that was implemented inside ImSwitch. So what you see here is the GUI, where you see blinking from our sample here, and all very low cost. And something I'm working on right here. So right now I'm in Manu Prakash's lab. Maybe some of you are familiar with him. He's one of the person behind the Foldscope project and many others. So our interest lays into visualizing the diversity of plankton from sea. And one way of doing that is using volumetric imaging methods. For example, light sheet. I think you may know light sheets. I think Emmanuel Rayon, he has a list of different abbreviations for the SPIM, the spin, whatsoever. So here are just some listed that can be recreated with UC2. I think that's like the open SPIM equivalent. So you can just bring that to schools and show what 3D really means in first microscopy. We had one where you have a flow through the objective that's basically cut by the light sheet, and then you just capture the 3D information over time, same with the open end. And something I would be keen on presenting you now, where ImSwitch becomes very important, is the holy sheet. We have a holographical and the light sheet detection all in one device. And so how does it work? So our idea was that we wanted to continuously sample plankton from the sea in a microfluidic manner, so that what you see here in the simulation have a rotating capillary, so that you gather 3D information over time, and then a constant flow, so that you have the light sheet information from, for example, autofluorescence, and then also the scattering in terms of holography. And so what we have here is 2 different cameras for the 2 different imaging modalities. We have an LED array for doing some kind of holography, so it's more intensity diffraction tomography. We have a laser to illuminate the sample from the side as a light sheet. Galvo mirrors, even though this changed now, to create the light sheet, and also the tube rotator besides the 2 C stages for focusing the objective lenses. And so in addition to that, you also want to have online image processing, so that you get from this 3D stack invest. So besides the optical setup itself, you of course also need electronics. You can just go to Texas Instruments and buy a bunch of expensive DAQ cards. We decided to take another route, following our idea of open source microscopy, doing open source electronics. And so we created a small electronic stack, which is also modular by itself, oriented around a small microcontroller called ESP32. And we asked the community what should be in there. And the result is now a small base plate that communicates to, for example, motor drivers. And on this little microcontroller, there's a unified code that's also thought to be modular, so that you can control different components very well conveniently by means of a REST API. So REST API, what does it mean? I think everybody is interacting with that all the time. It's just not very visible. So every time you open a browser, the browser sends HTTP requests back and forth, it gets information back. And so we thought it might be very interesting to just follow this idea of having microscopy oriented around this framework, because it's unified and rather simple to implement and accessible from many, many different platforms. Also following the idea from Richard Bowman's OpenFlexure, which is basically moving using the same principle. And so what you have here is the ESP32 interacts as a web server, which hosts some kind of a web page. In this case, it's a standard code open API, summarized by Swagger, as I think that's now a company. And what you have here is basically the ability to have a small website that summarizes the different properties of, for example, a motor, and you can send back and forth information. And so we implemented the way that it can be done through different channels, either USB serial or HTTP, so that you can have, for example, multiple ESPs connected to your clients. So the beauty of this Swagger is that you can just automatically export different clients, let it be MATLAB, Python, Java, whatever, JavaScript. And so with this, you can interact with almost any programming language, including ImSwitch. So everything here is open source. So it's an early stage project. So we are definitely looking for feedback, so that people find bugs and also contribute to the whole open source idea. You can find it under our repository openuc2/use2rest. And I now would also like to give you at least a brief introduction into how the holy sheet really works. So on the holy left, you see one fluorescence result from ALSI, the reconstruction, which was supported by Robert Hase. And I'll give you a quick tour or demo on the actual setup. Thank you very much.
Well, so hello. I am also very curious what this whole holy sheet is all about. It's sitting right in front of me. And what this is built of is mostly these little cubes. So the UC2 cube is now injection molded, but you can also 3D print it, and the idea is that you have basically the function inside the cube. You put them together. For example, here's a kinematic mirror mount, you have lens holders, and so then you just stack them together, a little bit like Lego, but you can also build very much more complicated setups like the holographical light sheet setup. And so what I'm going to do now is going to give you a little tour how it's going to work. There's a little syringe pump over here. I can control that through the PS3 controller that's basically just connected to the ESP32 through Bluetooth, or I do that with the ImSwitch that's running in the background. And so we have a bunch of sensors connected and also actuators. For example, you can rotate the capillary and also move the syringe pump. So when I move the syringe pump, the samples pump through the capillary that's then being rotated, and with this you can continuously measure plankton. So that's something we're interested in, so that we can measure the 3D information from plankton from sea, not only from the autofluorescence but also from the scattering. Hence we wanted to have the holographical part where there's just a single LED illuminating the sample so that you can measure the scattering on a secondary camera. So we have two cameras, we have three different actuators, being pump, the rotator and the focusing stage, and we have a pressure sensor so that we can introduce a feedback loop inside the microfluidics part. And so when I initiate the pumping, you will see that on the screen there are some parts going through it, the pressure goes up as well. So we will go to automatic mode so that we can just move the sample forward continuously and also rotate. And while the sample is rotating and samples are going through, the sample makes a spiral through the static light sheet, and then with this you will gather 3D information over time. So then the image processing that's not yet implemented here in the ImSwitch then does the reconstruction.